experimental robot learning with accelerated neuroevolution. Interesting talk. The speaker is Ahmed Ali. Ahmed Ali is a PhD candidate at the University of Virginia. He's actively working on alternative optimization algorithms for deep neural networks. His research goal is to develop technologies that enable robots to learn online from experience.
Thank you for the introduction. Hi everyone. It's great to be here. First, I want to say that the nature of our work is exploratory. The nature of our work is exploratory. We try to take risks and look into underexplored areas. This comes at a cost, though, of not producing or beating state-of-the-art results and not having shiny demos to look at least at the early stages of the work. So let's examine the title of the paper. The first part is experiential robot learning, and the second part is accelerated neuroevolution. So what is experiential robot learning? Experiential robot learning, ERL for short, is an approach that we developed in an attempt to accelerate the rate of development for robotics. By identifying scalability as a prime challenge in robotics, we usually need to handcraft robots to become experts in a particular domain. And an example of that is the Atlas robot by Boston Dynamics that performs like very flashy parkour moves. However, those same robots would typically struggle to do anything that they're not prepared for. In this light, we need to deliver a custom solution to every single domain where we want our robots to operate. So for those reasons, we outlined this method, ERL, to develop robots with the capacity to learn from experience, either unsupervised or weakly supervised. Learning should be open-ended online and in the physical world on device. So this is all previous work, but it's necessary to give you context. To understand the second part of the title, Accelerated Neuroevolution, we need to first present what we call the robotics development stack. This is from our perspective, which may be different for other groups. It represents hierarchical levels of abstraction that we typically encounter when developing robots. At the top is the sensory intake API. Those are streams from the environment and are typically noisy and unstable. So occasionally we may have to do some signal processing to work with those streams. Then there's the decision level API. Based on the input from the environment, what should the agent do? Now at this stage in our work, it's too early to work at this layer simply because our work is not mature yet. However, we're looking right into the layer that's after that, which we call the action policy API. So once the agent decides what to do, for example, let's say it wants to walk towards an object, how does that decision translate into physical action? So recently there has been a lot of work on using neural nets to encode the action policy. To do so, most of the research efforts have been directed towards reinforcement learning. In our experience, and maybe in yours too, we found that RL to be extremely frustrating to work with, especially when using RL in the framework of experiential robot learning, the method that we just described. So things were just not working for us. We reached the conclusion that our problem is not actually with reinforcement learning, but it lies deeper in the stack. It is in the optimization algorithm itself, namely stochastic gradient descent and its variance. SGD imposes the requirement of differentiability end-to-end, and it wasn't really developed to solve the kinds of problems that we're looking at in the ways that we want to solve them in. So we started developing our own line of optimization algorithms, starting with accelerated neuroevolution, which is what I'm going to talk about today. So there's a common saying that if all you had is a hammer, then every problem becomes a nail. What we're looking to do is provide another hammer, another tool for the researcher who's trying to develop robotics. It doesn't have to compete with gradient descent, especially in problems where the gradient space is informative, like MNIST or ImageNet, for example. Neuroevolution is a family of algorithms that is based on the concept of evolutionary optimization to train deep neural networks. In a sense, it uses trial and error to find a set of desirable weights for whatever task you want. It doesn't require differentiability, and thus a single optimization step can be computationally efficient. Optimization occurs over steps, just like SGD, and those steps are called generations. Across generations, we test out groups of populations, which we call a pool, and we keep improving upon them to reach the best solution. So now that we have a general idea about neuroevolution, let's talk about the algorithm itself. For the sake of time, I'll only introduce the most important mechanisms in the algorithm. First is mutation resistance. So mutation resistance is a number that governs the scale and the magnitude of mutations within the weights of the neural network. The search space here is the space of real numbers as represented by 32-bit floats for the weights of the network. Excuse me. In the diagram on the right, this dashed circle, we represent an abstraction of the search space. And of course, we all know that the search space is extremely high dimensional. However, for an abstraction from an abstract view, we can represent it as a 2D dashed circle. In it, the blue circle in the middle represents the origin, which can be an arbitrary location. It doesn't have to be in the middle. The concentric circles represent a radial expansion mechanism that occurs as the mutation resistance decreases with every generation. So now that we know mutation resistance, the second mechanism is pool composition. Pool composition is one of the most important and underexplored aspects of evolutionary algorithms. For us, every member of the pool is a costly addition. So we aim to minimize the size of the pool while still achieving the task in a reasonable amount of time. In our algorithm, the pool is composed of three main elements. First is the winner. This is the best performing agent across the generation, and it's typically called the elite in other literature as well. Carrying over the winner means that we never lose our best agent. The second group are the mutated clones of the winner. This group is typically small, representing slight variations on the winner's weights, hoping to exploit whatever region of the search space that this winner has found. Finally, the remainder of the pool is given to the offspring, which are the product of crossover. So as you see, we employ both mutation and crossover simultaneously, allowing us to explore new regions as well as try to exploit already known regions of the search space. So after developing this, our main question was, does this work at all? And the answer is yes. We tested the algorithm to solve the video game Flappy Bird. It's a simulated environment. It's fairly low dimensional, both in observation space and solution space. It means that the algorithm, if it's competent at all, it should be able to solve this, and it does. In the picture on the slide, you see the multiple birds, each bird being controlled by a separate neural network, and the bird that survives the longest gets the highest score. We tested this algorithm against a traditional genetic algorithm, employing only crossovers. And we know there's a great increase in performance from the algorithm that we used, up to a 7x improvement in learning time. So now our question was fine. It seems to work at a base level, but can we actually use it to train a robot? And here we need to take caution. Since this is a very new algorithm, we didn't want to go out and test it on a complicated problem because it most definitely will fail. We know that we can't use it to teach our robots parkour moves just yet. But we still needed a proof of concept. So we used the algorithm to discover a hard-coded policy online in real time. The policy solves a made-up task of centering an object in the robot's field of view. So to accomplish this, we used an SGD-trained convolutional neural network, which we called LocationNet, to predict the location of an object within a robot's field of view. And then the robot's task was to move its head left or right, so it's a single degree of freedom, until it predicts the prediction of the location changes to center, and then the robot should stop moving its head once the object is in the center location. So, to the best of our knowledge, this is the first hybrid architecture of networks that were trained with different algorithms and used in this way for online physical learning. In the experiment, each neural network in the pool would get a chance to control the robot's joints for 5 episodes. It gets a reward or a penalty based on whether it performed the correct action or not. And we were quite satisfied that the robot had zero knowledge about the task, but it was able to discover the policy in a few minutes of trial and error. So, conclusion, what can we get out of this? First, we created a new algorithm that's based on neuroevolution to train deep neural nets. We needed this kind of algorithm because we want our robots to learn in a specific way that is difficult to achieve using stochastic gradient descent. While we're proud of it, Accelerated Neuroevolution is only a first step. It will require a lot of effort to get it to the next level. The mechanisms introduced in the algorithm that we talked about do represent an advantage over vanilla approach, but there's definitely more room for innovation and competition. Finally, using our approach, what we really did is create a paradigm shift from how to use RL and stochastic gradient descent to how to improve the optimization algorithm itself. And even if we had a perfect optimization algorithm, we still need to find a good way to encode our task as a policy for the robot to discover. With that, I conclude my talk, and thank you very much.
Questions? So at the end, you talked about experiment by robot. So what robot did you use and what sort of physical experiment did you conduct?
I use a now humanoid robot. It's a miniature. It was shown a little bit earlier by one of the speakers. It's a small humanoid shape. The experiment was basically to move the head in a single degree of freedom according to the predictions that the CNN was producing based on the location of an object in the robot's field of view. So the policy was to center the robot's head to center the robot's head in relation to the object. Yes.
What fitness function do you use? Is it the distance from the center view you use to penalize or reward the genetic algorithm?
Yeah, so this task is fairly simple to encode as a policy. So all you need to do is you have basically three actions, either look left or right, or move the head left or right, or just stop. So whenever the robot produces a wrong action, so let's say the robot sees that the object is on the right and it's trying to look on the left, you give it a penalty there. So the neural net gets 5 episodes of control. So for each episode of those, you either assign a reward or a penalty based on the action from the robot.
But the now robot, I remember the cameras are one on the top and one on the bottom of its head. So, like, in more realistic case, like left and right eye, this, stereo vision, do you think that will play a factor on optimizing the head motion, with your algorithm?
I can't see that playing together, especially because they're aligned, the cameras are aligned to look at very different angles. Maybe it's possible, but from the work I do, we're mainly concerned with just 2D images without stereoscopic vision.
Thank you.
Any others? Okay. Oh, please.
Yeah. I have a question about ERL. I think it's a problem setting, right? Actually, what is the main feature for this kind of problem? I think you list a number of them. Are all of them the features to define the problem as not a regular reinforcement learning problem, but a particular ERL problem? What's the major difference here?
That's a good question. So I think the main differences would be physical learning in real time on the device without any sort of simulation. Bootstrapping, I put a note there, is fine if you want to pre-train your agent, but it really has to have the autonomous capacity to learn on its own. Usually in typical reinforcement learning, you don't see that sort of policy. If you want to update the robot's controller, you have to take the robot out of, or either out of the simulation environment, out of production, and then perform some optimization to the policy and then ship it back. So our method focuses on physical learning on the device as one of the features.
I see one of the results you've shown is a video game.
Yes.
So is that considered as a simulator or a real world?
The video game was just to test the algorithm, the optimization algorithm itself, not experiential robot learning.
Okay, thank you very much.